This is a video about the rule of 72, or as it's also known, the rule of 70 or the rule of 69.3. The rule of 72 is a rule that's used in finance and economics and banking in order to determine how long it will take for a given amount of principal to double in value according to the interest rates that govern it. Okay, so the formula that we look at here is F is equal to P star, the star indicating multiplication, bracket 1 plus I bracket to the power of n. The F is the future value, P is the present value, and I is the interest rate expressed as a decimal. So for example, if it's 5%, it's 0.05, and n is the number of periods over which the amount is compounded. So as we look at this, the first line here is F is equal to P multiplied by 1 plus I. So for example, if the interest rate is 5%, we would have 1 plus 0.05 or 1.05, and we would be multiplying the principal by 1.05 to find out the increase in value after 1 year. Okay, so the next line we have F is equal to P multiplied by 1 plus I, multiplied again by 1 plus I. Because after the first year, we multiply by 1 plus I. After the second year, we're multiplying again by 1 plus I. And this is where the 1 plus I to the power of n comes. By laws of indices, when we multiply a base by the same base, we simply add the powers. So for example, 1 plus I to the power of 1 multiplied by 1 plus I to the power of 1 becomes 1 plus I to the power of 1 plus 1, which is 2, as we see here. Okay, for the next line, we have future value is equal to present value multiplied by 1 plus I to the power of 2 multiplied by 1 plus I. So by the same rule as above, we have base to one power times the same base to another power, which gives us that base to the sum of those two powers. So we have 1 plus I to the 2 times 1 plus I to the 1, which becomes 1 plus I to the 2 plus 1, or 1 plus I to the 3. So looking at these terms, F is the future value of the amount invested. P is the present value, that is, at the time that the money is invested. I is the interest rate, which, as I said before, is expressed as a decimal. So, for example, if it's 5%, it would be 0.05. So when we add it to 1, we get 1.05. And if we multiply the present amount by 1.05, of course, because we're multiplying by a figure greater than 1, it will increase. The last letter in this equation is the n, which reflects the number of interest periods. Typically, interest is calculated per annum or by year, so it reflects the number of years that the amount is compounded for. At this point, I want to take the most basic case where we invest $1 and we want to see how long it takes for that $1 to become $2. It could be 100 becoming 200 or 1,000 becoming 2,000, but we'll use 1 and 2. And when we calculate this, we'll be able to come up with the rule that shows us how we find the length of time it takes for this to happen. So looking at our formula, we've substituted on the left-hand side for F2, and we've substituted on the right-hand side at the front of the right-hand side, 1 for P. And if we step down to the next line, multiplying anything by 1, we can simply remove it if the coefficient is 1. So we have 2 is equal to 1 plus I to the power of n. Okay, the next step is to take logs of both sides. So we've taken the natural log of both sides. And we will see why we do this in the next step, due to the convenience of using logarithms when we have powers. Okay, so going to the next step, if we take the log of 2, we get 0.693 to 3 decimal places on the left-hand side. And on the right-hand side, we can rearrange that expression given one of the properties of logs. If we have, as you can see in green on the right of the page, the log of bracket a to the power of b bracket, one of the properties of logs is that we can rearrange that. as b times log of a. So the power becomes a coefficient for the log of the base. Now the next step here, the left-hand side stays the same, but on the right-hand side, I've changed the expression from n times log of 1 plus I to n times I. The critical realization here is that for small values of I, log of 1 plus I is almost equal to I. And we'll look at why that's true by examining graphs of this to see what the error is. Now, looking at the graph of these two functions, I've changed these to use mathematical variables. So instead of I, I've put x. So we have the first function, which is y is equal to log of 1 plus x, which is in red. And then the second function, y equals x, which is in blue. Now, looking at positive values of x, we don't need to worry about negative values. As we go along the positive x-axis from 0 outward, we can see the divergence between the red curve and the blue line, which touches the red curve. It's tangent to the red curve at x equals 0. But as x gets greater and greater, the blue curve, the blue line diverges away from the red curve. And that becomes apparent that we can't use that as an approximation, but that's only for very large values. So we're going to examine values of x, or values of I, for which the approximation is very good. Okay, so I've blown this up a little bit, and we're now looking at values of less than x equals 1. So we'll concentrate on 0.5 or less. For what it's worth, the 0.5, if x is equal to 0.5, that's the equivalent of I equals 0.5, which is 50%. So that would be for an interest rate of 50%, which is almost unheard of. But as you can see, as we get closer and closer to the origin, those two curves get closer and closer together. So we'll look even more closely at this to see how the error shows up. Now, looking at this third slide of the graph, we've zoomed right in for x values of less than 0.2. And if we consider 0.2, which equates to a 20% interest rate, we can see that the error from log of 1 plus x to x is just 1 part in 9. So already it's very good. And if we look at 0.1, we can see that it's even less. So here I've highlighted 0.2, or 20% interest, the point at which this occurs. But you can see the error is small enough that we don't really need to worry about this. But mostly we'll be dealing with far lower rates of interest than this. Therefore the accuracy will be good. And here we are looking at x equals 0.1, which corresponds to a 10% interest rate. So the approximation is between 0.1 and natural log of 1.1, which when you work it out, the error is less than 5%. So getting back to our formula, we can see now we were up to 0.693 over I, where I was written as a decimal. So if I was 5%, it would be 0.05. So we would have had 0.693 divided by 0.05. So what we've done here in this step is to multiply that fraction on the left-hand side, to multiply the numerator and denominator by 100. So instead of 0.693, we get 69.3 for the numerator. And instead of 0.05, if it's 5%, for I, we write I as a percentage. So we write that as 5. Note that 69.3 divided by 5 is exactly the same as 0.693 divided by 0.05. The only thing that's happened here is that I've turned this around so that we have the subject, n, on the left-hand side, which is what we typically do. N is equal to 69.3 over I as a percentage. And that brings us to the last step, which is to have changed 69.3 to 72. Why? Well, 72 is close to 69.3, and 69.3 has no factors, almost, but 72 has a multitude of factors. So you can easily divide this if you've got some numerical skill without picking up a calculator. So almost any interest rate can be reasonably quickly divided into 72 mentally. So here are the factors of 72. 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, and 72. Or another way to do this is to pair them up. 1 times 72, 72, so 1 and 72, 2 and 36, 3 and 24, 4 and 18, 6 and 12, and 8 and 9. Notice that when we find the factors of a number, we only need to go up to the square root of that number. If we're pairing factors, then we've found everything we need. So for example, if we're looking at the factors of 100, the square root of 100 is 10. So we only need to go 1 and 100, 2 and 50, 4 and 25, 5 and 20, 6 doesn't go, 7 doesn't go, 8 doesn't go, 9 doesn't go, 10 is multiplied by 10. And since we're up to the square root, we don't need to go any further because we've paired all the pairs of we've found all the pairs of factors we need. So as I was saying before, the first pair highlighted is 1 and 72. The second pair highlighted is 2 and 36. The third pair highlighted is 3 and 24. The fourth pair highlighted is 4 and 18. The fifth pair highlighted is 6 and 12. And the last pair is 8 and 9. So to finish off, we'll do another simple example to see how this works. So if we consider, again, the most basic case where we have a present day value of $1, we want to see how long it will take for that to double if we have an interest rate of 3%. So just filling in the values, we have P equals 1. We have I is equal to 0.03, which is the decimal form of 3%. And we want the future value to be 2, and we want to figure out what n is in order for this amount to double. So exactly as I mentioned before, at some point in the future, this amount will have doubled. F is 2, P is 1. We're searching for the value of n for this to be the case. So we start off with substitutions, so 2 for F, 1 for P, and 0.03 for I. So we have 2 is equal to 1 times bracket 1 plus 0.03 bracket to the power of n. So for the next step, I've just removed the coefficient of 1 multiplying what's in the brackets. We then calculate the logarithm of both sides. So just rearranging here using the rules of logarithms, the left-hand side of this equation stays the same, the right-hand side changes. So log of bracket 1 plus 0.03 to the power of n becomes n times log bracket 1 plus 0.03. Okay, the next step is this important substitution. So the right-hand side, which is n times log of 1 plus 0.03, becomes n times 0.03. This is where, as I've noted down below, for small I, we can use the approximation log of 1 plus I is equal to I. So that reduces in the next line to n is equal to log of 2 over 0.03. And just for the sake of following what I did before, I've multiplied both the numerator and denominator of that fraction by 100. So we get 69.3 over 3. Although you could simply calculate that, use a calculator to work out that value now. Now the last thing I've done since this video is about the rule of 72 is to use 72. So I've put that as 72 over 3. So that's approximately, but very close to 69.3 over 3. And we'll see something very nice in the next shot. So we can see, as we noted before, that one of the factors of 72 is 3. So 72 divided by 3 is equal to 24, as is the case with many numbers, which happen to be factors of 72. But even if we had a number which wasn't a factor, say for example 5, we could still note that 72 divided by 5 is the same as 72 divided by 10 multiplied by 2, and 72 divided by 10 would be 7.2, multiplied by 2, 14.4. So 72 works out very well because of the number of factors and also because of other tricks that we can use to work out how numbers divide into larger numbers. So, to summarize, if we have an amount and we receive 3% interest per annum that compounds annually, it will take 24 years for that amount of principal to double. And currently, with interest rates being around 1 or less, around 1%, that means it will take much, much longer for doubling to occur. Another thing to notice is that figure of 24, if we take 1 plus I, or 1 plus 0.03 in this case, which is 1.03, and we raise it to the power of 24, that will give us a result which is just over 2, which is the multiplier that we wanted, to multiply the original amount of $1 to make it $2. So if you have a calculator, you can just try that and you'll be able to see. So by raising it to that power, 1.03, we've changed that into a factor very close to 2. So hopefully that gives some illumination onto what the rule of 72 is and how it works and how we actually derive it in order to figure out the length of time it takes for a given amount with a given interest rate to double. Okay, recap. F is equal to P times 1 plus I to the n. F is the future value, P is the present value, I is the interest rate, and n is the number of periods the interest is paid out. So for simplest substitution to find the doubling time, we substitute 2 for F, 1 for P. So we have 2 is equal to 1 times 1 plus I to the power of n. Next line, 2 is equal to 1 plus I to the n. Then we take log of both sides. Log 2 equals log 1 plus I to the n. Log of 2 is equal to 0.693, and we use the rules of logs for the right-hand side. Log 1 plus I to the n becomes n times log 1 plus I. The next step, we have 0.693 is equal to n times I, using the fact that I is almost exactly equal to log of 1 plus I for small values of I. Next step, n is equal to 0.693 over I. Next step, we multiply the right-hand side, the numerator and denominator, by 100. So we still have the same ratio. N is equal to 69.3 over I as a percentage instead of a decimal. Final step, we substitute 72 for 69.3, given that 72 has many factors. N equals 72 over I %. Thank you for watching this, and I hope it was useful in giving some understanding of how this rule is derived that's used in finance and investment. I'll be uploading videos more typically in the field of pure maths, and I'll be doing that as frequently as I can. If you enjoyed this, feel free to subscribe and follow me at Michael Angland Maths. Thank you.